We're going to jump right back in today with a section 11.1 basic notions. And we had just gotten through with example number 3. Talking about lines and planes. So we're going to look a little bit more today at lines and planes. Two planes can be either parallel or intersecting. There aren't any other choices. If they're parallel, they have no points in common. You might kind of jot down an example for you. It would be like the floor and the ceiling. Those would be models of parallel planes, the floor and the ceiling. If two planes are intersecting, that could be the model as the wall and the ceiling. Now, when they do intersect, what do they intersect in? Can you imagine the wall and the ceiling? Where do they intersect? A corner, but just one corner? What do you mean by corner? Maybe I should have you describe that. What is the corner in geometry representing? A point, a line, a plane? Those are the only kind of objects we've talked about. What is it? A point. Okay, so you mean a corner like that little corner right over there, right? Okay, so but if we did the ceiling and the wall, is that little corner over there the only place that they would intersect? It would actually be the line. It would be the line all the way across the front of the room that is both on the floor or on the ceiling and the wall, right? So if they do intersect, they would intersect in a line. We'll get to that in a minute. Oh, I didn't because it says it on the screen. I'm sorry. The intersection is a line. So that's your visual imagery, right? It's the line that would go along the floor. I keep saying floor. I should have used floor as my example. Along the ceiling and the wall. A line, when you compare a line and a plane to one another, it can do one of three things. It could be parallel. If it's parallel, it doesn't have any points in common. It could be intersecting. If it intersects it, it could be contained in it, like it's actually in that plane, or it could be cutting through it, and it intersects in only one point. So let me give you visual imageries as well in our classroom. You can jot them down for reference if you would like. If you were talking about a parallel line and plane, you can imagine my ceiling as my plane, okay? And you can imagine any line that's in our floor as our line. Okay, we've got this grooved floor here. So just take one of these carpet grooves all the way across, and that line would be parallel to the ceiling. Agreed? That's one possibility. We'll keep going with our ceiling as our plane. So if we have the ceiling as our plane, we could have a line that's actually contained in the ceiling. We have ceiling tiles. Again, follow one of these lines or these, imagery of the line on the ceiling, and that line would actually be inside of the plane that is the ceiling. Right? So that would be a line contained in the ceiling or contained in the plane. Another possibility is that we have, again, my ceiling as my plane, and then the line would be something like this edge that goes all the way from the floor to the ceiling. It intersects the ceiling, right? But only at that very corner point. It's not inside of the ceiling. It's not a plane that has the line inside of it. The line is on the outside of it, but it does cross through it. So those are the ways that we can actually have lines and plane comparisons. Now, getting a little bit more specific, we could talk about not just intersecting things, but how they intersect. For example, perpendicular. We can talk about perpendicular lines and planes. Perpendicular lines are lines that form right angles where they intersect. And this amazing backdrop that I'm going to use this whole semester in this class has lots of perpendicular lines, doesn't it? That's how we create grids. Usually they're perpendicular. So all of these grid markings here, and I'll draw one in just for good measure. So if I have this particular part and this one, they're perpendicular to one another because they form a right angle. And a right angle can be marked like that little corner box. And the notation for how that is written is that we have the line, we have that perpendicular symbol, that's a perpendicular symbol to the other line K. So if you will, this could be L and this can be K. A line could also be perpendicular to the plane if it's perpendicular to every line in the plane. Now my example earlier where I had the plane as the ceiling and the line as this edge between my walls that goes up through the ceiling, that would be perpendicular. And the reason is because when it intersects the ceiling, it intersects the ceiling at a right angle. Because it's a right angle to this line in the ceiling and it's a right angle to this line in the ceiling. Every place where it's intersecting and it has a line there, it's perpendicular to that line. So that would be a line perpendicular to a plane. And then we can talk about two planes being perpendicular if the angle formed when they intersect is also a right angle. And as a reference as well, I mean, this is how we build buildings, right? Is we build perpendiculars all over the place. So our ceiling and our walls form right angles unless things start settling and shifting. And you've maybe been in houses where they're a little bit crooked. That wouldn't be perpendicular, but these would. Okay, so two planes are perpendicular if we get that right angle in their corner. Okay, so let's talk a little bit more then about angles because I keep referencing right angle in my last description. An angle is formed when two rays share an endpoint. So do I have the picture in your paper? If not, please draw it in. Okay. So here's our picture of an angle. The blue lines on my screen are the rays. They start at this thing that's called vertex. It's labeled point B. And it extends upwards through point A. And it extends horizontally through point C. So those are two rays, ray BA and ray BC, that are forming the edges or the sides of our angle. They have a shared endpoint called the vertex. The part that's kind of shaded in, I don't know, almost orange there or peach, that is the interior of the angle. And it doesn't really end. I mean, the picture has to end because we can't draw it infinitely. But everything, you know, these rays keep extending. This shaded part keeps extending. So it's not actually a triangle. It looks sort of like they've drawn a triangle there. It isn't. It's just you can only shade so much of a picture before you're out of space, okay? So the interior is all of that space inside. So we don't define it, but can you imagine what would be defined as the exterior? Yeah, all the space that's not shaded and it's on the outside, right? You bet. Okay, a little bit more about angles. We're going to talk about measuring them in a minute. Angles are named by a number. So sometimes you'll call angle 1, angle 2. A Greek letter. My image here has Greek letters alpha and beta in it. Or 3 points. So I'm going to write down the two angles. There's 3 angles actually that are here. So the 3 points would be the vertex, and then a point on each of the rays. That would create an angle. So there are angles here that could be referenced like this. We can talk about angle alpha. Okay? Well, another angle that is equivalent to, it's exactly the same angle as angle alpha, that another name for it, is we could talk about this angle QPR. It's important that the P is in the middle because it's the vertex. So that's like a requirement. But I didn't have to write QPR. Any other thoughts about what I could write? RPQ. Those are exactly the same angle. They're written differently, but these are all 3 names for the same angle that's on my screen. And just to clarify, I'll use it in yellow at the bottom. It's this angle that I'm talking about. I just kind of drew that sloppy, but you got the idea. Okay, multiple names for the same thing. And that happens a lot in geometry, a lot, where we have multiple names for the same thing. We call 2 angles adjacent if they share a common side, a common vertex, but no part of their interior. So this image here has adjacent angles. The 2 adjacent angles are alpha and beta. Oh, blue is a bad choice because it's already drawn in blue. How about green? Alpha and beta are adjacent angles. They're adjacent because they satisfy all these conditions. They share a mutual side, right? The side that they share is ray PQ. They share the endpoint, the vertex, right? P. And they don't overlap each other. So, in other words, what you can't do is you can't say that I've got this angle and I've got this angle and they're adjacent because they overlap, right? Likewise, I couldn't say I've got this angle and I've got this angle. They actually even share a side and a vertex, but they still overlap. So those would not be called adjacent. Adjacent means side by side, okay? Now let's talk about measuring angles. It's going to be really important. I want you to write yourself in big, bold, highlighted, colored in red. I don't care what you do. We're working in degrees, and we're going to work in degrees only, which means that if you're talking about the measure of angle, you need to have the degree symbol on there. It's the unit for what we're talking about. One of the common measurements for an angle's opening is in degrees. The notation looks like you would have expected, of course. Because a full rotation of a circle is 360 degrees, 1 degree would be 1/360th of a circle. We can break degrees down into smaller quantities. There are 60 minutes in a degree. And we can break down minutes into smaller quantities. There are 60 seconds in a minute. And there's sort of an analogous thing that we do with minutes and seconds on a clock, right? 60 seconds in a minute, 60 minutes in an hour. So it's done with the same scaling that we do for a clock, which is kind of nice because the clock's also circular. So that's actually pretty friendly. Minutes have 1 mark, and seconds use 2 marks. All right. So let's talk a little bit more about minutes and seconds and how we go between minutes and seconds with degrees and decimals with degrees. So our first example, number 4 on here, is to take something that's given in a decimal value, right, 0.46 of degrees, and turn it into minutes and seconds. All right? The process is not difficult, but you do need to remember which way you're going. That's going to be the catch for some people, is remembering, do I multiply or do I divide? So on this one, the 32 at the beginning is already in degrees, so we don't mess with it. It is 32 degrees. It's going to be 32 degrees. It's the 0.46 that we're wanting to change. So what do? Well, here's what we do. We take the 0.46 and we multiply it by 60 because there are 60 minutes in a degree. So, right, this is almost half a degree, right? 0.46 is about half. If you were rounding, you might even round it to 0.5, right? So if we think that we're dealing with the minutes this way, we'd expect that this should give me about 30 minutes. Agreed? Because that's about half a 60. So grab your calculator and tell me what you get when you multiply, sorry, that should have said minutes. When you multiply 0.46 times 60. And keep your calculator out. We'll use it a couple more times here before we're done. 0.46 times 60. Ooh, we get a decimal again. Okay, so 27.6, this is my number of minutes. Okay? 27.6, that's pretty close to 30. So does that seem like a reasonable number? It should. It should seem reasonable. But we've still got a decimal point, the 0.6. All right, so now I've got 32 degrees, and I've got 27 minutes. And the last piece is the 0.6. How many seconds are in a minute? It's not a trick question, I promise. 60. Yeah, there are 60 seconds in a minute. So we're going to multiply the 0.6 one more time by 60. We're turning minutes, 0.6 minutes, into seconds. Now again, this should be more than half, right? 0.6 of 60, 0.6 times 60 should be more than 30. So if your calculator is giving you something else, you've probably entered it in there wrong. So I've got my 32 minutes. I've got my 32 degrees, 27 minutes. And what is 0.6 times 60?
36.
36, even?
Yes.
Excellent. 36 seconds. 32 degrees, 27 minutes, 36 seconds. This is exactly what you would do if you were talking about, I don't know if any of you have watches when you do running or athletics events, things like that, and you're wanting to know how fast you are. Usually your watch will report it in minutes if you're doing a short distance in minutes, and it'll have a decimal point number of minutes, right? That decimal point is not your seconds. So if it reports like this, 32.46, that does not mean 32 minutes, 46 seconds, right, in that scenario. If you wanted to know how many seconds you had, you would take the 0.46 times 60 to figure out how many seconds that took you. It's the same idea as that you would do with a running watch. Okay, we're going to go the other direction now. Now we're going to start with the degrees, minutes, seconds, and we're going to turn it into a decimal point of a degree. Now, the 48 is still going to be 48. I don't need to deal with it at all. It's already in degrees. And this says 57 minutes. Okay, that's almost 60, right? Yeah? I mean, so this is almost like 49 degrees. Are you guys with me? I mean, 57 minutes is like on a clock. That's almost an hour. In fact, you probably would say it is an hour. You probably wouldn't even say 57 minutes, right? Unless you were running and your watch says 57 minutes when you're done, and then you're going to say 57 minutes. Okay? All right, so let's take a look at how we would do this. If I multiply by 60 to turn it into the minutes and seconds, what do you think I'm going to do to pull it out of the minutes and seconds back into degrees? Divide. Exactly right. So we're going to do that. We're going to leave the 48, right? As we mentioned before, 48 degrees is already 48 degrees. And then we're going to take the 57 and we're going to divide by 60. Now you may notice I haven't dealt with the 36 yet. I will. But is everybody good so far with the 57 over 60? Okay. Now I could put the 36 over 60 as well, but that would be the same as turning it into minutes. Seconds into minutes would be dividing by 60. So what do you think I might be dividing 36 by instead? Twice. I need to divide it by 60 twice. So in a very real sense, I'm going to divide it by 60 squared. It's 60 twice. It is 3,600. Oh, I'm sorry. You mean the number on top. My bad. You're right. Thank you. 36. This is what I was talking about. The 60 squared is the same thing as 3,600. So, okay. So grab your calculator. You can actually put this in a scientific calculator straight from left to right. Obviously, you don't have a degree symbol, but you can write 48 plus 57 over 60 plus 36 over 60 squared in most of your calculators. And it will do the proper order of operations and calculate it all at once. If not, find each piece, write them down, and then add them together when you're done. Now, it should be almost 49 when we're done. That's what it should be. We already talked about the reasonableness of what our expectation is. So what do you guys get? 48 point what? 96 degrees. Is that almost 49? You couldn't get much closer, right? Yeah, you couldn't. Because 57 minutes was also really already close to a degree, like it would be close to an hour. All right. I'm going to do an example of subtraction. Your book, when you're doing your group work and your homework, you're going to have some examples with addition as well. It works very similarly. The question asks us, what happens when we take an angle of measure 89 degrees, 37 minutes, 24 seconds, and we take away an angle of 48 degrees, 57 minutes, 21 seconds? And you may not have ever done this with degrees, minutes, seconds before, but you've probably done it like that on a clock, where you've either added time or subtracted time, and you've turned your minutes into hours or your hours back into minutes to figure out the difference of things. Okay, so it's the same idea. We're going to write it much like you would write an addition problem when you're in early elementary grades, where you're writing it on top of each other. So we're going to start there. We're going to write 89 degrees. Leave yourself a little space above this, too. Don't write it right beside the words. Leave yourself some space. 37 minutes, 24 seconds. And in this problem, we're subtracting 48 degrees, 57 minutes, and 21 seconds. Okay, does everybody have it sort of set up in corresponding rows, if you will, so far, columns? Okay, great. Now, just like with addition and subtraction in early grades, it's easiest, it's not the only way to do it, but it's easiest and usually taught this way if you start on the right-hand side for the subtraction. So if I had 24 seconds and I took away 21 seconds, how many seconds did I have? 3 seconds. You bet. And that's all fine and good until you get to the minutes column. I have 37 minutes and I want to take away 57 minutes. Well, there's a problem, right? And so what would you do if you were in elementary school, ignore the degrees, minutes, seconds, or whatever, and you need to do the subtraction? What operation would you do? Borrowing. And just for a heads up, they don't call it borrowing anymore in most textbooks. They call it regrouping. Okay, I know because my kid keeps bringing home papers that say regrouping and my husband's confused. Like it's just borrowing. They call it regrouping. And the reason they call it regrouping is because, let's just think about it in terms of like ones and tens. If you're borrowing a 1 from the tens column, you're turning 1 10 into 10 ones. So you're regrouping what the value actually is. That's why they call it that. It's a little bit more mathematically accurate what you're actually doing. We can call it borrowing, I don't care. All right, so here's the deal. I need to borrow. I don't have enough minutes. So if I go over to the column on the left that has the 89 degrees and I borrow a degree, how many degrees will I have left? 88. Okay, so I'm always borrowing 1. But if I borrow a degree, what is its equivalent value in minutes?
60.
It's 60. So don't go adding 1 to the 37. You didn't borrow 1 degree. You didn't borrow 1 minute. You borrowed 1 degree. And 1 degree is 60 minutes. So this 37 actually becomes what? 97. The 37 minutes that were there before plus 60 more minutes. And now you can subtract. What's 57 minutes taken away from 97 minutes?
40.
So that would be 40 minutes. So we have our 40 here. And then 88 minutes minus 48 minutes, 88 degrees minus 48 degrees would be 40 degrees. And there's a note on the bottom here as well. It says, as long as your values for minutes and seconds are between 0 and 60. And are they? Yes. Then you're done. Now, what will happen is when you do addition, sometimes that won't be the case. Maybe your answer ends up giving you 65 minutes. Well, if there's 65 minutes, you're going to need to, the word that we are going to use or should be using is regroup that into degrees, right? 65 minutes would be 1 degree and 5 minutes. And so you would regroup it appropriately, or instead of borrow, you would carry. That's actually how it would work. All right, different types of angles. We have 4 types of angles. I've actually got them all drawn in here. Do you have pictures on your paper? Nope. Okay, then I will pause and keep quiet for just a minute while you draw my 4 pictures. If you will draw them as number 1, 2, 3, and 4, then we can all reference them that way. That would be helpful. Okay, so what we're going to do is we're going to label these angles as 4 different types of angles. Does anybody remember on the first one what that kind of an angle is called? Acute. And usually people say, it's just so cute. And they remember it that way. So if that helps you, you're welcome. This is an acute angle. So this one is acute. We'll go out of order. Does anybody remember what number 4 is? That one is the obtuse. How about number 3? What is it?
Right.
It's a right angle. We've already talked about that one today, right? See what I did there? I used the word right when I said right. It's clever, right? Right? All right, how about number 2?
Straight.
It's called a straight angle. It's kind of weird because we also would call that angle a line, but it is technically called a straight angle. Whoops, I should spell it correctly. And just as a reference point, your book doesn't talk about them, but you might end up with a book at some point that does, and you'll be like, I never heard it called that before. When you have an angle like this on the outside of this, right, like it sort of goes backwards and it's actually more than 180 degrees, it's called a reflex angle. So if you want to jot that down, you're welcome to. Your book doesn't call it that, but I would hate for you to find it somewhere else and go, my teacher never taught me that. It is called a reflex angle. Reflex, yeah, like your reflexes, yeah. All right, the last piece that we're going to work on today is going to be some vocabulary related to circles. So by definition, a circle is the set of all points in a plane that are the same distance, that distance is called the radius, from a single point, and that single point is called the center. So one of the things I want you to sort of take into account here is that the center of the circle is not actually part of the circle. All right? The circle is just that outer edge that you see drawn. That's it. An arc of the circle is any part of the circle that can be drawn without lifting your pencil. That's one of those intuitive definitions. It's not really mathematical, but intuitively that's what it is. So there's no distance that it has to be as a minimum or a maximum. It just means that you don't go all the way around and you didn't lift your pencil to do it. So an example of an arc here would be arc AB. There's also an arc AC. There would be an arc CD. There would be an arc DA. So notationally, it looks like this when you write it. If I were talking about an arc, I would write down AC, just like I were talking about the line segment AC, but I put an arc above them instead of a line segment or a line above them. So this would mean arc AC, whereas this would actually mean segment AC, as in it's a line, portion of a line, right? This would be line AC. This would mean ray AC. And I take the time to write all those out because I want to make sure that you don't just write down AC. Because there's a lot of things that it could be if you just write down the letters AC. And actually, if you just write down AC, what it means is the distance. We talked about this last time. From A to C. In other words, it's a numerical value. It's not even a geometric object. Okay, so be real careful with your notations because they really mean different things. What's the center of this circle? It's O. Yes, it is. And if we were talking about the radius, there's a lot of them we could write down, but can you give me an example of one of the radius or radii of my circle? What would it be? Okay, OD or DO. And we put the line segment on top of it because a radius is a line segment. Could I write down OC? Would that be right? Yeah? Any letter O, not any letter O, but O with any letter, that's what I meant to say, on the circle would be considered a radius. And it doesn't matter which order I write them in, so like CO is the same as OC. Okay, so those are interchangeable. Those are the same line segment, same radii. Arcs. Okay, we talked about arcs in the last screen, so let's talk a little bit more about them here. Each pair of points on the circle determines 2 arcs. The shorter one is called the minor arc, and it's sometimes labeled with only 2 points. The longer arc is called the major arc, and it's always named with 3 points. And if the major and minor arcs are the same size, we'd have semicircles. So let's go back and actually add in some of those from this particular diagram. So if the diagram's not drawn on your paper, if you would draw it in real quick. Somebody give me an arc in this diagram that you believe is a minor arc. CA. And in referencing CA, I believe you're talking about this piece. Is that true? Good. Yes, we can call the minor arc, one of them in this, CA. And again, put the arc on the top of it, right? Make it look curvy. Mine's sketchy on the curviness of it, but it's not too bad. CA. Is there another name for CA? Arc CA? Arc AC. Okay, so those would be the same thing. Let's take that same CA and let's go the other direction. That is to say, let's talk about going right here instead, where I've got the green drawn in. That'd be called the major arc AC. The problem is if I only write down AC, you wouldn't know. So if it's a major arc, the way we distinguish that from the minor arc is that I can write my AC, but I need a letter that's between them as I go around the circle. So if I go from A around to C or C around to A, what could I write as a point that we pass through between? D or B that are currently labeled. So take your pick, write it in between, and then put the arc on top of that. This would be the major arc AC. So with the minor arc AC, we've got the major arc AC. Now, that example is not a semicircle because they're not the same, right? Arc CA and arc ADC, they aren't the same measure. One's longer than the other one. Can you give me an example of two arcs here that are the same? ACD. And unfortunately, my diagram doesn't have another point listed on it, so let's just put that in there so we have a reference point, okay? What letter do you want to give this point a name as? Let's go with K for Krista. I had a student I tutored one time, and she always used letters that were her and her friends' names. That's what she did. This is point K. All right, so we could actually call the other direction of this arc what? Okay, well, KD would only be, whoops, KD would only be this part of it, right? What can we call it? AKD. These would be semicircles for this particular diagram. All right. I think this is our last definition for today, chord. A chord is a segment connecting 2 points on a circle. So this is a segment, not an arc, it's a segment. If a chord happens to run through the center of the circle, we call it a diameter. So can someone give me an example of a chord on this diagram that's not the diameter? Somebody said it. CA. And what should I draw on top of CA to represent the chord? A line without the arrows. Good. So a segment notation like that, right? Yeah, that's a chord. CA or AC with the segment notation on top is a chord of this circle. Now, it's actually true that DA is also a chord. Okay, but we can define it a little bit more precisely by calling it a diameter because it's a chord that runs through the center. So this would be a diameter DA. We see this happen, this sort of a definitional difference. It wouldn't be wrong to call it a chord. It's actually not wrong to call a square a rectangle. You might feel uncomfortable about that, and it's okay. But it actually fits the definition, and we'll get to that later this semester. But a square is a rectangle. But square is a more precise description, right? It gives you extra information, just like diameter here gets you extra information. You know it goes through the center.